Hi everyone, welcome back to Algorismo. Today we are going to explore linear search. Quite literally, the search we use every day, whether it's finding your keys, looking for a name in a list, or searching through files. This fundamental algorithm is at the heart of our daily routines. Let's dive in and see why it's so indispensable. In our first video, we laid the foundation by discussing what algorithms are, step by step procedures for solving problems. We introduced a simple problem to find the students with maximum grade from the list of given grades. We then discussed how to express the algorithms beginning with simple pseudocode, and then writing the same using Python. Then we organized our code as find max function. In the exercise, we used the same find max function to explore the concept of complexity analysis, where we saw how the number of steps or operations grow with the size of input. Let's quickly revisit the complexity analysis of find max function. Here's the code. The key part to note is the loop that checks each element in the list to determine if it's the maximum. This operation's complexity is directly influenced by the input size because for every additional element in the list, the algorithm performs one more comparison. Therefore, the loop at line 3 will execute n times for a list of length n, whereas line 1, 2, and 6 will execute only once no matter what the input size is. One consideration here is how many times the lines 4 and 5 execute. Since these are part of the loop, let's for the sake of simplicity assume they also execute n times. We will come back to formalize this concept later. Summing all these steps results in 3n plus 3 as the total number of steps this algorithm will take to find the maximum number from a list of size n. To simplify further, we can say that as the number of elements in the input list grow, 3n plus 3 is dominated by n, and the effect of constants does not change. Again, if this looks confusing, don't worry. As we move on, we shall formalize this concept too. Putting it simply, for a list of size n, the total steps are roughly n. This is what we call a linear relationship. If the list size doubles, the number of operations also double. Formally, we can say that the complexity of find max algorithm is big O of n, where we simply ignore any constants and coefficients of the polynomial. We shall define this big O notation soon. Understanding this notion of step count or complexity helps us evaluate the efficiency of algorithms, which is crucial when working with large amount of data. Let's write our linear search algorithm. The algorithm to find the maximum number was named the find max algorithm. Similarly, we name our search algorithm linear search, an apt name that clearly reflects its functionality. For the find max algorithm, the input was a list of numbers. For linear search, the input is also a list of numbers, but we add an additional input, the target value we are searching for within that list. The output of the find max algorithm is straightforward. It returns the maximum number found in the list. In contrast, the output of the linear search is the position of the target value within the list, or -1 if the target is not found. This indicates whether and where the target exists in the list. As both algorithms begin, in find max, we initialize a variable max to the first element in the list. In linear search, there is no need for such initialization. Our focus is solely on finding a match for the target value, so we skip this step. Next, in find max, we loop through each number in the list. This loop allows us to compare every element to our current max to see if it's larger. Similarly, in linear search, we also loop through each number in the list. However, instead of looking for a larger number, we are searching for an exact match with the target value. Within the loop in find max, we compared the current number to max. If current number was greater than max, we updated max to show the new value. In linear search, rather than checking if the current number is greater, we check if it equals the target value. If a match is found, we return the index of the current element immediately, not executing the loop any further. But how to return the index? We will turn to it shortly. After the loop completes in find max, the algorithm returns the max value, which is the largest number found in the list. In linear search, if the loop completes without finding the target, we return -1 to indicate that the target is not present in the list. That's it. In summary, both findmax and linear search algorithms share a similar structure, but their goals and internal logic differ slightly. By following a similar approach by adapting the logic, we can see how algorithms can be tailored to solve different problems. You may pause and notice the differences highlighted in linear search compared to the findmax algorithm. Let's move on to the implementation. On the left, we have the findmax function as before. On the right, we begin writing the linear search function. Just like in findmax, we start by defining the function with its input parameters. In linear search, these parameters are the list of numbers and the target value we are searching for. As we move on, both functions use a loop to iterate through the list. In findmax, the loop checks if each number is greater than the current maximum. In contrast, linear search checks if each number matches the target value. If a match is found, the function returns the result immediately. Notice how this mirrors the comparison step in findmax, but instead of updating a maximum value, linear search is focused on identifying and returning the position of the target. The question mark you see is what we will shortly handle to return the position or index. If the loop completes without finding a match, linear search returns -1, indicating the target isn't in the list. Finally, to demonstrate the function, we use a sample list and a target value, printing out the result to show where the target is found, calling linear search within the print statement. Now let's refine our linear search function to make it easier to return the position of the target. Instead of using a simple for loop to iterate through the numbers, we will switch to a range-based loop. This loop allows us to work with the index directly, which is crucial for returning the position of the target in the list. The range on length of numbers expression generates a sequence of indices from 0 to the length of list -1. By iterating over these indices, we can access both the index and the corresponding element in the list. This is different from our previous loop, where we only accessed the elements directly without knowing their positions. Let's break down how this refined loop works. First, for each index I in the range of the list's length, we check whether the element at that index equals the target. If a match is found, the function immediately returns the index I, which gives us the exact position of the target in the list. If the loop completes without finding the target, we return -1, indicating that the target is not present in the list. By using the range-based loop, we enhance the linear search function's ability to not only determine if the target exists, but also to provide the specific location of the target within the list. This refinement is particularly useful when the position of the element is as important as finding the element itself. Now let's further refine our linear search function to make the output more informative and user-friendly. So far, we directly print the result of the linear search function, which shows the position if the target is found or a -1 if it isn't. While this worked, it doesn't clearly communicate whether the target is found or not in a way that's easy to understand. To improve this, we will first store the result of the linear search function in a variable called index. This allows us to check the result before deciding what to print. If index equals -1, it means the target wasn't found in the list, so we print a message saying the target is not found. This makes it clear to the user that the search was unsuccessful. On the other hand, if index is not -1, it means the target was found and we can print a message specifying the exact location like this. The target is found at location specified by the index. This approach makes the output much more informative and user friendly, clearly distinguishing between a successful and an unsuccessful search. In our final refinement, we will improve the flexibility of our linear search by allowing the user to specify the target value rather than hard coding it in the code. Previously, we set the target value directly using a statement like target is assigned 1. While this worked, it's limited because the target is fixed within the code. To make our function more dynamic and interactive, we will replace this with a statement that prompts the user to enter the number they want to search for. We use this input function which asks the user to type a number. This input is then converted into an integer by wrapping the input function into int function. This small change makes our program much more versatile. Now, the user can search for any number they choose without having to modify the code itself. This refinement is particularly useful in real-world applications where the data we are working with can vary each time the program runs. It's a great example of how we can take a simple algorithm and adapt it to be more user-friendly and applicable in different scenarios. Let's see linear search in action. We are here on Python tutor website, and here is our code. Let's walk through the execution of our code step by step using Python tutor. The first line defines the function linear search, but the control does not enter the function yet. Instead, the function is stored in memory, ready to be called later. Next, control moves to line 7, where we define sample list, a list containing the numbers 5, 3, 9, 1, 6. This list will be the data we search through. The control then moves to line 8, where the program prompts the user to enter a number to search. Let's input 1 here. On line 9, the linear search function is called with sample list and target as arguments. Control now enters the function starting at line 2, where a loop is initiated using range on the length of numbers. This loop will iterate over the indices of the list, allowing us to check each element. On the first iteration of the loop, I is 0 and control moves to line 3. The function checks if the element at index 0, which is 5, equals 1, which is the target. Since it doesn't match, control moves back to line 2 for next iteration. On next iteration, the value of I is 1 and the element at location 1 is 3. And on comparing 3 with 1, it is again not the target that we intend. So the control will move back to line 2 again, and now I will increment to 2. Again, on 2 we find 9. It does not match 1. We go back to 2 again, and now I is incremented to 3. At location 3, the item is 1. That is what we are looking for. So in this case, the condition on line 3 will turn out to be true, and we will move on to see that line 4 will return the index of this location. So that is 3 that is returned to the function call that was made at line 9. So the control exits the loop and the function, returning to line 9. Back at line 10, the program checks if the index is -1. In this case, index is not -1 because we were able to find the target number in the list and we got the actual index of that number, which is 3. So that means the if condition will turn out to be false. And finally, at line 13, the program prints the target is found at location 3, confirming that the target 1 was located at index 3 in the list. Let's analyze the complexity of the linear search function by counting the steps involved. We start with the first line where the function is defined. This line does not depend on the input size, so it takes a constant 1 step. Next, we move to the loop. The loop iterates over the list, checking each element to see if it matches the target. Since the loop runs once for each element in the list, it can take up to n steps, where n is the number of elements in the list. Now, this is true only in what we call the worst case. The worst case occurs when the target is either at the very end of the list or not in the list at all. In these situations, the loop has to check every single element before finishing, or on the other hand, there is also a best case. The best case happens when the target is found at the very first position in the list. In this scenario, the loop only needs to run once, taking just one step. In the exercise, you will be able to play with these cases. Inside the loop, there is an if statement that checks if the current element matches the target. This condition is checked every time the loop runs. If a match is found, the function immediately returns the index of that element. No matter when this return statement is executed, it will execute only once because the function does not continue once the return statement is executed anywhere inside the function. In the best case, this return happens after just when the target is at the beginning of the list. In the worst case, the return happens after n steps, either because the target is at the end of the list or it isn't found at all, leading to the final return statement outside the loop. So after the loop, if the target wasn't found, the function returns -1. This final check also takes a constant 1 step. When we sum up these steps, in the worst case, the total number of steps can be represented as 2n plus 3. As we did for our findmax algorithm, in big O notation, this simplifies to O of n. Big O simply ignores all the constants and coefficients. This means the time complexity of linear search function is linear in the worst case, just like the findmax algorithm. In the best case, however, the time complexity is O of 1 because the search completes after a single comparison. In general, as the input size increases, the time it takes to complete the search grows proportionally in the worst case. This means that for every additional element in the list, the number of operations required by the algorithm increases by 1. As the input size grows, the algorithm's time complexity increases at a constant rate, resulting in linear growth. You will have more to explore about the worst and best cases in the exercise associated with this video. You will also find a third case, the average case. Well, a lot of information. Don't worry, we shall unroll these concepts again in our future videos. Let's recap what we covered today. We analyzed the step count or complexity of our findmax algorithm. We also briefly defined the big O notation and hope to solidify the concept as we move forward. We then took a deep dive into the linear search algorithm, comparing it to the findmax algorithm to highlight their similarities. From there, we defined our linear search code, making it more robust and user-friendly. To wrap up, we conducted a complexity analysis, exploring how linear search performs in best case and worst case scenarios. With all this knowledge at your fingertips, it's time to apply what you have learned. We have prepared an exercise for you on GitHub. Link is provided in the video description. This exercise will challenge you to explore the step counts of linear search in different scenarios, from the best case to the worst case. By working through it, you will solidify your understanding and gain practical insights into how the algorithm behaves in various situations. So make sure to check it out and put your skills to the test. Coming up next, we'll explore binary search, an algorithm that takes search efficiency to a whole new level. While linear search checks elements one by one, binary search is much faster. But there is a catch: it only works on sorted lists. By continually halving the search range, binary search quickly zeroes in on the target, making it a vital tool in algorithm design. Don't miss our next video, where we will break down how binary search works and why it's such a game changer. That's all for now. Thank you for watching and joining me on this journey through algorithms. Don't forget to check out the code examples and exercises on our GitHub page. Your feedback is important to us, so please share your thoughts and suggestions in the comments. See you next time for our lesson on binary search. Happy coding!